Good afternoon. Today's topic is synthesis of thiophene, and like previous topic, thiophene synthesis is again an important area, but you have to justify what are the importance, and very quickly let us have a little bit of the look at the importance of these categories of the compounds. Do you have any idea? Can you prompt me on this aspect, whether why they are so important? Thiophene, where have you come across the importance of thiophene? See, like pyrols, there are plenty of natural products, then polymers, etc. Furans, they are very important reactive intermediates. So similarly, so likewise, thiophene actually do not figure in natural products. There are very few natural products which will have a thiophene nucleus. On the other hand, they are very useful as a polymer. If you remember, last time I talked about, there is a polymer called PEDOT, that polyethylene dioxythiophene, which is produced in tons and tons, and this polymer is of paramount importance in the field of organic transistors, then organic light emitting diode, what we call OLED, and there are several applications actually as a conducting polymers, and sometimes we call organic metals. Okay, these polythiophenes are known as organic metals. Okay, so that means they are pretty important. In addition, I think many of you know a large number of thiophene derivatives are nice organic intermediates, and then one of them is pretty popular solvent. Many of you probably heard of a material called sulfonel, right? And this is sulfonel. What is it used for? It is basically an organic solvent. It is an organic solvent. Then there is a molecule also probably you know of, which is nothing but it is known as I think many of you know. What is it? It is 3-sulfonil, and it is there are ways to look at it. This is called solid butadiene. In fact, butadiene can be combined with sulfur dioxide to produce a nice solid. So both the gases immediately react with each other and forms the solid, and this can be stored in solid form for years and years. In fact, if you like to see, I have a bottle of this, a big bottle, quite nice powder. Okay, it is basically a source of small scale preparation of butadiene. So one can just take these and heat it at around 140 degrees, so you can get the butadiene. Otherwise, you have to buy a huge big cylinders. Okay, so in small scale, one can quickly generate this one. And what else? You can actually, for example, you can derivatize. You can derivatize by using an LDA and then alkyl halide. You can convert this into this one. Then if you heat it, of course, what you will be getting? You will be getting the substituted butadiene. So that means they are very important reactive source. And similarly, many of you probably know what can be done with this thiophene. Thiophene also is a nice starting point for diel solder. Is not that popular though in thiophene case. It is not very like furan case. It is not very popular because most of us know the thiophene is the most aromatic nucleus in this series. Okay, but what can be done very quickly in one or two steps? One can produce a branch or long chain alkanes. How do you produce? Not yes, reduction. Actually, what one can do, first you have to derivatize two corresponding, let us say you can produce something like this, right. So, Friedel-Crafts reaction kind of things, and it undergoes reactions at 2 position. Then you do the reduction, and you can do the reduction, let us say normally with runny nickel. So, what you can get? You can get a product which would be looking like, let us say this looking at it. That means you will have a long chain hydrocarbon kind of compounds from this sort of materials. Okay. So, today what we do, we will take up different synthetic methods, and based on normally the starting materials. And so, the first one, sometime it is once again it is known as a Paul synthesis, not its Paul nor or anything like that, Paul synthesis. So, the name tells you and what should be the starting material, right. The starting material should be 1,4-diketone, and then the reagents, and that would give you in one step the corresponding this one. And what is the reagent? The commonest reagent is, I think many of you know, P2O5, right, P2O5. So, P2O5, P2S5, and what is the so intermediates? Actually there is an exchange of sulfur with the oxygen. So, what you will be getting? You will be getting, so I mean this is assumed, but it is not isolated. Then like regular kind of thing. So, what you will be getting? You will be getting sort of an intermediate thiol kind of things, and then as usual for aromatizations you lose H2S. So, you get to this one. Only disadvantage with this method, many of you probably do not know, a little drastic too reactive reactant. Okay, P2F is a pretty reactive reagent, number 1. Number 2 is an inorganic material. So, it does not tend to dissolve in organic solvent. So, it's sort of like heterogeneous reaction, and the best way to circumvent this problem, you have to use a sort of a hybrid kind of reagent. And the reagent which is very popular in this area is, I do not know how many of you know of this reagent. This is known as Lave-Hessen reagent. Okay. And what is it? It is basically an organic molecule then coupled with P2S5, and which starts from anisole, then you will link with phosphorus, then this again sulfur, then phosphorus, again one more nucleus of anisole, that would give rise to a nice yellow crystalline solid, and anybody can do it. In fact, we used to make it on a regular basis, this compound. It is known as a Thiophene reagent. That means this reagent is very popular to convert a ketone to corresponding thione. Like say, let us say you have benzophenone, and you want to convert this into thionobenzophenone or thioketones of benzophenone. How do you do it? P2F is perfectly all right, but this is the best way, as I said, it is nicely soluble in organic solvent, and it is manageable, and it is not that reactive. Okay. So, this is one of the best way to and then you can also try with this, let us say bis trimethyl silyl sulfite, like this one. This is also can be useful again in the presence of P2S5. Okay. So, just I will give you just one or two more examples of this synthesis and why it is so useful. Like say if you start with a thiophene containing compounds, and then again a ketone, and then the ketone has to be 1,4, and then once again you have a thiophene. So, you do, I will just from now onward I will write ALR, Lave-Hessen reagent, and so first thing what you do, if you start with this and then react with RBr, that means it is an alkyl halide, and KOH. I will tell you why we need all these things, and a DMSO is a solvent because you are using KOH, and then use these Lavoisian reagent. So, what do you expect here? You can expect here that now thiophene derivative with 3 nuclei, and then this is R here, and then so what you will find here, you will get 3 different kinds of nuclei. Why we are doing so? Because as I told you before to start with, that oligothiophene are very useful as semiconductors or conducting materials. Okay. So, this is the way one can make the actual, that means the Lavoisian reagent is useful for thiophene containing 1,4-diketone, and but before you do the formation of the thiophene, what you do, you have done an alkylation with regular KOH and DMSO to introduce an R group in the nucleus. The reason being, so if you have a large alkyl group, I think polymer chemist would know it has an advantage. What is the advantage? Have an alkyl side chain in a monomer. Solubility. Best thing would be best thing people say processibility. So processibility would be the better term for the in polymer chemists. Okay. So, you can go on, then let us say okay, I mean these are all important. Let us say then you let us say you use acetic anhydride and phosphoric acid. So, what can you guess here? What can you guess here? Acylation. So, that means you will get this acylation done at 2 ends. The 2 ends, the middle one of course, you do not have any the 2 and 5 positions are blocked. So, one can have an acylation on the 2 end sides, right. So, you can go on doing all these things, and what next? In fact, from this onward, I mean you can do Mannich reaction. I mean just I am just giving you an example how to grow on this original molecule with more thiophene nuclei. So, you can convert this into I will just very quickly write this thiophene and then this, and you can just quickly do the Mannich reaction. So, all of us know Mannich reactions would give you this homologation by 1 carbon, right. So, similarly on this side also you will give the homologations this. Now, from here you can generate again 1,4-diketone with Michael addition with thiazolidine salt, that is stator reaction. Stator reactions, Benzyl thiazolidine salt like the potassium cyanide. Okay. So, when we do synthesize this benzoin kind of things, in case of alpha beta unsaturated ketones, it gives you 1,4-diketone. So, then you can go on doing this and eventually get to the oligomers. In this example what I was citing, it has produced 11 mers. 11 mers means, I think all of you understand, means there are total of 11 nuclei of thiophene. Okay. So, that means this is the way, that means this is analogous to all other pyrrole and furan nuclei synthesis. Only thing you have to remember the reagents. In this case, what is new we have learned, this is Lavoisian reagent. The other way to go to this thiophene system is a method called Hinsberg synthesis. Hinsberg synthesis, it is nothing but it is a pretty simple synthesis based on aldol type of condensation, condensations. If you have 2 ketones, 1 2 diketones for example, AR and AR, and so one can just think about a bis acetate, thio-bis acetate or thiodiacetate you can say. If you take thiodiacetate with the sulfur in these. So, that is what you have to remember, in this case diacetate, and this reagent of course, all of you can guess what could be the reagent. Reagent could be this is a strong base, and normally potassium tertiary butoxide is used in combination with that is a butanol, and in, the temperature here is around 60 degree centigrade, and all of you can guess what is the product. The product would be a thiophene here, Ar and Ar, then as a methyl here and a carboxylic acid. Little tricky though, you see only one has got hydrolyzed and the other is remaining intact. If you have come across such things are seen in a very famous reaction in carbon elongation process. Anybody knows this reaction? Stowaway condensation. Remember, it is a reaction with what? Benzaldehyde and benzaldehyde and right, succinate. So, you get a half ester. Okay. So, there you also, so a very similar reaction mechanism that you get that. Okay. Next thing that I think from now on what we will do, we will go by the sulfur containing compound that is used in the synthesis. Okay. So, the previous one was bisacetate or thioacetate. Okay. And the other next one will be thioglycolic acid. Thioglycolic acid means basically all of us know glycolic acid is OH-CH2 and thioglycolic acid ester is okay, this one like okay. And so, what you can see here sulfur, carbon, sulfur, sulfur and carbon, that means one sulfur and one carbon is provided for the nucleus, and this is one of the commonest starting material in making these thiophenes. Like I will give you an example here. Let us say if you have cyclohexanone and one can readily convert this into this compound, right, homologate compound. I will not tell you, maybe I will come back and ask you the same questions. Now, if you react with this thioglycolic acid ester, methyl thioglycolate, and in the presence of catalytic amount of sulfuric acid, so what do you expect out here is little different than all other glycolic acid etc. Sulfur has a propensity to undergo aldol condensations, wrong or right? Normally sulfur actually prefers to undergo conjugate additions because of the large size and so okay. So, what one would expect here, that means alpha beta position would be attacked by sulfur, then followed by elimination of water. So, you are expecting an basically acid catalyzed condensation, acid catalyzed Michael condensation kind of thing here. So, once you have this, then you can guess in the previous example what was it? It was Hinsberg method, it was had a lot of like aldol condensation kind of thing. So, in this case if you use sodium methoxide, so the methoxide, once again methoxide means the other solvent is methanol. So, what do you expect? A kind of aldol condensation kind of thing, aldol condensation. So, you will be getting a fused thiophene, and of course, one of the substituent is an ester here. So, I mean they are all somewhat like standard now. For example, I mean if you just extend this, for example, you can do an extension of these like that was an alpha beta unsaturated compound, and now you can start from these acetylenic compound. So, in this example what I have here, this is basically one more substituent on this side, then react with thioglycolate, methyl thioglycolate, and you do not have to do anything here, by the way. It is so reactive to the thioglycolate is so reactive at 0 degree centigrade, just simply mix them, you can expect a Michael reaction. You can expect a Michael reactions with sulfur then CH2, and then here is an ester here, and then whatever you had before, that is the other groups here, other groups here. Okay. So, just a Michael addition. Now, you know the stage is ready now. So, you do the aldol condensation between the carbon and the carbonyl of this line, and that would require a base. In this particular example, the base was CGM carbonate, CGM carbonate. So, the product would be then just you can write this is a thiophene unit, and then you have this ester which comes from the thioglycolic acid R and the double bond, and then you have the other substituents what you had here OR and OR, that is the ketal substituent. So, I mean this is a standard protocol actually, this is a standard protocol. If now if you do not want to have the carboxylic acid like esters here, what you have to do, you have to just hydrolyze and then do decarboxylation. Decarboxylation, that is not that easy, but it requires very high temperature, copper quinoline method, right. Carboxylic acid, copper quinoline, that gives you the decarboxylation. And just to refresh your memory, how do you convert this into the hydroxymethylene compound? Who can tell me quickly? This one I am talking about, this conversion. This is a standard actually way of, that means it is alpha formoyl cyclohexanone. How do you make it? There are two ways to make. One is to just take sodium hydride and well, there are then three methods then. Actually methyl format or ethyl format, okay, you can use. Then dimethyl carbonate you can use, dimethyl carbonate, okay, that would give the corresponding formal derivative, or actually that actually gives the corresponding ester derivative. Best thing would be if you take dimethyl carbonate, that will give the corresponding ester derivative, but it is the aldehyde derivative. So, best thing would be the this methyl format or ethyl format, okay. So, what is the other possible sulfur source? So, we have seen P2S5 Lavoisian reagent, and then the thioesters, thioglycolic esters, bisacetates. Okay. What are the other possible sulfur source? Sulfur with carbon is one of the cheapest. C. Good, very good. So, we will look at it how it is used. So, that means one can use, in fact, there are plenty of examples. The CH2 has been exclusive, I mean rather not extensively been used in heterocyclic chemistry. Okay. So, if you take with start with what is that, what is this malononitrile, and take let us say potassium hydride and then carbon disulfide, you do not have to actually take potassium hydride. In fact, simple potassium hydroxide would I have to check, I think I made a mistake somewhere here, it should be even potassium hydroxide should be perfectly alright. Okay. Because dimethyl malononitrile is so active, okay. So, what do you expect here? You get a kind of a thioenolate kind of thing, thioenolate. And then with the equivalent amount of alkyl iodide, in this case let us say methyl iodide. So, one can just selectively S-methylate one of these S minus and these, and then the other remains as S minus. Next thing that you want that has been done here in this example, use this chloroacetone, and what is expected, chloroacetone, what is expected here unlike those furan synthesis. If you see try to recollect in the furan synthesis, the reaction normally goes first with this aldol condensation, but here is sulfur you have here. Sulfur has a tendency, it is a softer nucleophile. So, actually it would displace this chlorine. So, what you will expect then SMe and then one sulfur, then this is the acetone part and this, and then you have this is cyano and this is cyano. Okay. So, this is now, and of course, once you have this, then what next under the basic condition, actually this is done in basic conditions, and basic conditions what you are expecting, an ion would be formed, then this cyanide would undergo the reaction. Okay. So, eventually after all this tautomalization, all these things isomerization, so he will be getting in this SMe here and aminothiophene. So, 3 aminothiophene and with acetyl side chain, acetyl side chain. Okay. So, so what is new? I mean what is to be known here or what is to be remembered here, that these cyanide groups is sufficiently reactive. Normally cyanides do not react with carbon nucleophile. Let us say if you have an acetonitrile, if you try to do it malonate kind of things, it does not undergo any reaction. Okay. Probably the reaction should take place elsewhere, but in this case it is a case of intermolecular reaction. So, cyanide opens up to become an amine group, and this is a very frequently observed reactions in heterocyclic chemistry. That is, cyanide could be an important source of amino group. Okay. So, if you have a requirement of amino substituted heterocycles, so you can think of cyanide as the source of nitrogen. Okay. And let me next let us say just we are giving one more example actually from how elemental sulfur. So long we have been using the sulfur compounds, sulfur carbon compounds, and now elemental sulfur also can be used to form thiophene, and this is a case this like in this example what you will see here, you start from a thiophene and with an alkyne side chain. Alkyne again we have seen it before, alkyne has been a very good precursor for heterocycle synthesis because of the cyclizations, okay, endocyclizations. Now, if you treat this with N-butyl lithium, of course at low temperature, I will just write low temperature, I think by now many of you know what is the expected reaction. Expected reaction should be lithiation or lithium exchange, lithium halogen exchange, that is the very first reaction, and that is what we would expect here. So, you will have this lithium halogen exchange, it is a very important reaction. And then if you take elemental sulfur is all of you know the structure, right, formula S8. So, S8 what do you expect here? Let us say if you have a let us say Grignard reagent, you treat with sulfur, what do you get? SH. So, initially what would do, it would form S here, right, then this 6, right. So, basically it will form a sulfide, then it breaks 6. So, it breaks down to this is unstable, of course, this is unstable. So, what you will be getting? You will be getting this S minus now, right, S minus and TMS, S minus and TMS. And then in the previous in furan cases you have seen this sort of this nucleus would undergo 5 endo cyclizations, and the process of workup would give you a compound which is of course would be known as thiophene. That means I mean this strategy, basically introductions of the lithium then converting this into corresponding sulfur minus, and then the process of basically acidic workup would desilylate and the compound to give you the corresponding thiophenol compound. And what is the chemistry part? The chemistry part is that once you have a S minus, that can undergo even unactivated alkynes to form the thiophene. So, I will give you one more example in similar to this one. For example, in this case, if you have let us say thiophene, like this, and let us say in other case I am writing exactly the way it was. So, something like this. Now, you treat this with sodium sulphide and aqueous methanol. Of course, in this case little heat is requiring. What do you expect? What is the expectations? Normally, we do not see any reaction done with alkynes with sulfur, right. So, sodium sulphide, but since there is a possibility of here is a ring closure of S minus, so it would undergo reactions. It would undergo reactions means several rather. So, we will get what we will get here, you will get a thiophene and so it is trinucleus thiophene. You can get, sorry, in this case you will get this here. So, that means 1 2, that means 1 2 3 4. So, sulfur minus would attack here, right. So, that is okay, and then it will again that means there are 2 minuses. So, it will undergo reactions with these. So, sulfur minus would I think there is a mistake somewhere here. It should be 2 5 substituted, the middle one should be 2 5 substituted, right. So, 1 2, yes, I think it should be 2 5 substituted, 2 5 substituted thiophene. So, that means basically trinuclear thiophene derivative would be produced. And there are other ways to use disulfide kind of things. Disulfide, this work has been published very recently. This was in 2010 Organic Letters, page number 3930, and this is very similar to the previous one. In this case, sodium sulphide was used, and in this case it is potassium sulphide in the presence of the transition metal, and the procedure goes like this, or the methods looks like this. It starts from a diiodo compound, then you have all kinds of R groups. It could be 1 2 3 4, all kinds of, this is basically a diiodo compound. Now, since it is an sp2 connected carbon connected iodine, it is not that reactive, but the source is instead of the sodium sulphide it is a potassium sulphide, I do not know why, but that does not work alone. So, what you have to do, you have to use a catalyst, and of course, whenever you have a copper, there is a chance you need a transition metal, and in this case 10% cuprous iodide, and temperature is around 140 degrees centigrade, and the solvent is acetonitrile, and the yield is very good and the reaction is very general. So, what you can get is now is a highly tetrasubstituted thiophene. Mind it, getting a heavily substituted nucleus is very difficult. Reason being, first one, introduction of first one is okay, second one is okay, third, fourth, as you go on you increase the steric effect. So, this is the reason why this sort of methods are developed. Okay. But apparently one would think that this method is not that very great. Reason being, reagent is pretty easy, right. So, substrate. So, substrate that means making the substrate is very difficult apparently, but there are ways to way out, because again this is due to Negishi all of you have heard the name Negishi coupling. This same Negishi, he has a reagent named Negishi reagent, that is Cp2 and zirconium. You know zirconium, the place in the periodic table below zirconium is below titanium. And what is it famous for? Actually, in organic chemistry, zirconium is very useful. Many a times it is used as a substitute of hydroboration reagent. Okay, suppose you want to do a very selective hydroboration and you are unable to do so. Okay, you can think about zirconium hydrochloride. Actually, that was a Cl and hydrogen. So, this just like hydroborating reagent, it can undergo hydrozirconation. Okay. So, this is the reagent. Now, if you react with the alkynes, these alkynes like say ethyl and ethyl alkynes, obviously pretty easy to make, and use 2 equivalents of butyl lithium, what you get is not a heterocycles, it is a zirconacene kind of, that means the zirconium here, then this is cyclopentazirconium, zirconio cyclopentadiene you can say, and then this is Cp, Cp and Cp, okay. And then this one should be ethyl and ethyl and ethyl here and ethyl here, okay. So, what next? So, and if you then if you use iodine and cuprous chloride, you can get this well defined diiodide substrate, diiodide substrate, that means pretty easy to make, and this is also very easy to make, that is not very difficult to make. Okay. So, that means there is a way out to this material. And we will come back to some of these problems for practice, but let me, I think I will give you one more important, very important way of getting the monomer for the oligothiophene and thiophenes. What I said before, there is a monomer called E dot. E dot stands for ethylene dioxy thiophene. What it is? It is a monomer for its corresponding polymer. So, P E dot means polyethylene dioxy, and it would look like this. Sorry, it would look like it would look this. So, how do you make this molecule? So, we have learned quite a bit of, right. So, we have learned quite a bit of sulfur chemistry and these things that. So, how do we make this? This compound is again produced in tons and tons, it is a conducting polymer. So, how do I know? Okay. So, that means the pol 1, it will give you the 2 5 disubstituted. Okay. The other from the thioglycolic acid, it will give you the carboxylic acid, you have to hydrolyze, you have to plenty of quinolines, decarboxylate, all these things. Okay. So,
Thiophene is produced from sulfur.
Thiophene. Okay.
There is the 3,4 substitution.
Okay.
In this case also the 3,4 substitution is required.
Thiophene will be
3,4 substitution.
Thiophene. Which method, let us say?
From sulfur,
S8. Okay. No, but here you have oxygen. Oxygen. Okay. So, that means what we have learned is not enough, we have to learn a little more, that is the that is the logic I am trying to bring to. Okay. So, that means something else is required, and in this case you start with a dimethoxybutadiene. Okay. Dimethoxybutadiene. So, I think once we have defined one of the starting material which provides 4 carbon atoms. So, what is the other reagent that we can think of? that means reagent is little new. Sulfur dichloride, and it gives straight away dimethoxy thiophene. Pretty easy, looks good, right? Looks good, and see here the temperature of the reaction is only 5 degrees centigrade. You mix them, these are such a nice one. And what next? What is even more important, many of us know that cyclization process is very facile, right? It is very facile when there is a possibility of cyclization, because it is an intermolecular reaction. And if you do this reaction with ethylene glycol in the presence of paratoluene sulfonic acid, just in I mean no time you will get this compound without any problem. Okay, just basically again a displacement sort of addition elimination reactions, eventually get to this compound, and the reaction is so powerful. In fact, this so this was known since 1990, around 95 or so, but then what can you do? Somebody published this very similar work known as Michael Bendikoff in 2008. How can you extend this reaction to elsewhere? That is what you have to know. See, when you say I have been telling about this thiophene throughout the last 20 minutes or sorry 40 minutes maybe. Okay. So, but then you have to say something new. So, similarly we are the research scholars, we are the researchers, we are the MSc students. Okay. So, what should we say? What could be the next example? That is what you have to think about, and what new chemistry you have learned. In this, for example, in this case you have what is the new thing you have learned? It is a new reagent. We have never come across any reactions of sulfur dichloride, right? We have not. So, like this. Okay. In the other area, let us say in the material chemistry for example. So, what can you think about? Like I know Amit is doing thiophene chemistry, and right, Saurabh is doing thiophene, he is not absent, he is absent today, he is also doing thiophene chemistry, but how can you extend your work to other areas? Guess? Okay. And he has published in JACS. Person who has followed this work, what he did? Selenium dichloride, exactly same thing he has done, but then sorry selenium here, okay, he has made these, only thing he did not stop here, he developed the method for the polymerizations, What he did, he reacted with NBS, and NBS would promote, yes, it supplies bromonium ion, but where does it go? You have so many places. Okay. Actually it undergoes, although NBS is known for benzylic brominations, right, but you do not have a benzylic carbon here, benzylic hydrogen. So, it undergoes nuclear brominations. So, you will have something like this. Okay. So, that means a dibromoselenophane. So, now that means our discussion was not restricted to thiophenes, also it can be selenophanes. Up to this was pretty okay, but you know this compound is unstable. In fact, unstable in but it gives a very interesting compound. Just if you heat it around 50 to 60 degree centigrade, it undergo polymerizations that they wanted. That means polyselenophane they wanted, and of course it gives improved properties, etc., etc., etc. So, that is the reason why it is published in JACS. Okay. So, we have, let us say we have talked about most of the things except one more important thing where we involve elemental sulfur, and the method is known as Gewalt synthesis. and where elemental sulfur is used, and the starting materials are it is let us say a ketone and malonitrile, then sulfur is used and amine as a base. So, amine as a base. So, what you will see, the product that is formed is then, I think one can think about it, easily visualize it. In this case, then you have NH2 and cyano, NH2 and cyano. Okay. So, again aminothiophenene, aminothiophenene. What is to be noted? That you are now deriving the amino group of the heterocycles from cyano. So, cyano is a good source of amine. Okay. And what else? Now, the elemental sulfur is incorporating, this sulfur of the thiophene. So, what is the reaction? I think all of us can agree that in the ketones and the diethyl malonate would give you this malonitrile would give something like this, Novagel kind of reaction. Fine. What next? How does this elemental sulfur undergoes incorporation? In the previous example, if you remember, there was a lithium compound. So, lithium basically nucleophilically attacked the sulfur bond, opened up the chain to make the sulfur minus, which decomposes to corresponding monosulfide. Okay. But here what do you expect? Here also a very similar thing, that was a carbon minus with lithium. In this case, you do not have a carbon ion here, but you can expect a carbon ion here, right, because it is a double bond, two cyanos are there. So, allylic positions could be a carbon ion. So, then of course, then you have a sulfur here, and so you can think about this is Cn and this is S8, probably S8 minus, and then slowly it would decompose to this monosulfide minus, and once you have a monosulfide minus, then you can go on writing this, I guess. I think all of us can write, right. So, it forms the imine, right, and then this deprotonation isomerization would give you the corresponding. This is called Gewald's amino synthesis. Okay. So, lastly, I think I should give you a reaction, a very interesting reaction. This is let us see whether you can predict the reaction mechanism. This is a case of thiophthalate and thionothiophthalate, I would say. Thiophthalate is something like this, which is called thiophthalate, and we have worked extensively on this. We have a reagent method by which we can use naphthalene out of it, and that method has been adapted for total synthesis. That means a thiophthalate can be a nice class of reagent for making fine chemicals, other chemicals. Okay. So, that way we can increase the importance of the thiophene nucleus. Now, if you treat this with again this well known reagent called Lavoisian reagent or Lavoisian reagent, what you get is now so thiono, because it is ketone is converted to sulfur. So, thionothiolite. So, how do you what do you see here? So, what is the reagent or what is the reaction mechanism? Reaction mechanism that has been proposed little unlikely, though it is not that straightforward. So, what is the first thing you think of in a such and this reaction happens to be pretty general. You take two more I mean other aldehydes, you will get similar compounds, quite general reaction. Okay. So, what is the first thing you can think about? First thing you can think about. Lavoisian reagent, what does it do? It exchanges this, right, is exchange right with sulfur here and sulfur here, and of course next thing, I mean, so that we thought it would give this thionoaldehyde. Probably you do not know, thionoaldehydes are very difficult to make, very difficult. I mean, there are very few stable thionoaldehydes. Okay. So, they are pretty unstable. So, then of course, one can visualize this, right. This one would go to, this is sulfur here, and is that all right? I think up to this looks okay. That means intramolecularly it forms a sort of deuterion kind of thing. So, or you can say elide kind of thing. Okay. What next you can think of? Because this is the product, right. So, this is the, if this is the product, then it has to be something like this. This hydrogen probably would be migrate to this one. So, if you do this hydride migration to this sort of a benzelium ion, benzylic cations here. So, you can get to this compound. This is the, I mean, tentatively proposed mechanism, but apparently it looks okay. I mean, there is no complaint about it, but I have only one complaint about it. What is the complaint? Can you think of any complaint against this mechanism? What is the complaint? What is rather striking about this mechanism? You have not seen before. See, all these hydride shapes, carbonium ion, everything they proceed in 1-2 manner. You will never, I mean, only occasionally you will see, very rarely you will see, right, 1-3. That is quite, I mean, normally it actually it goes through non-classical carbonium ion, etc., etc. So, 1-2 is more favored and logically expected, but 1-3 maybe intramolecularly this reaction is taking place. That is a possibility. That is not tested yet. Okay. So, summary, time for summary. Thiophene nucleus. I have missed one important point about thiophene, about natural products. For example, have you heard of the term called biotene? Who has heard the name biotene? Raise hand. Okay, only one. Mona Lisa, oh good. Okay, Subhendu, what is it? Huh? No, you are a chemist now, right? When I say what is quinine, you say it is a natural product, that is not enough. Whenever you want to claim yourself as a chemist, then you have to tell me the structure or structural features. Okay. Mona Lisa, what is biotene? Structure. Okay, Korobi, it is a thiophene derivative. It is a thiophene derivative, but well, it is arguable. Some people can say it is an imidazole derivative. Let us say something like this. Then you have 1, 2, 3, 4, 5. Levulinic acid derivative. So, that is it. So, if these are hydrogens are beta, it is pretty easy to remember, but you know why it is so important, that is you have to know. I can claim this as a thiophene derivative, and if you look at the top portion, then you will see that this is an imidazole derivative, but well, so that depends on your advantage. Okay, for today's class, I think this is thiophene derivative, and so but tell me, what is the use? Actually, it is very good. Actually, it is a good nutrient for humankind. Okay. In fact, for animal also it is implied that animal health is improved if the sufficient biotene content is there in their animal food. Okay. Moreover, many of people do not know, if you lose hair, there is a chance, especially the girls. If you, so, actually you may lack biotin content. So, you have to supplement your food with biotins. Okay. And there are many other things. For example, I mean so some people say also it is good for those who are diabetic, diabetes patient. Okay. So, I mean there are, okay. So, summarily, okay, in summarizing thing, okay. So we have seen this Paul synthesis that based on these P2S5 and its derivatives, that is Lavoisier reagent. Then thioglycolic acid is one of the important, right, reagent from where you can do. Then elemental sulfur can be made use of, and then some diiodide substrate, olefinic substrate with organotransition metal that can be used, and that Gewalt also synthesis that it involves the elemental sulfur. Okay. What else? One more, right? Sulfur dichloride. Sulfur dichloride also can be used for synthesizing substituted thiophene derivative. Fine. Okay. Let us see how much you have learned. Test. Okay. Tell me the answer of this sequence of reaction. We begin with acetophenone, POCl3, DMF, you get a substrate here, then thioglycolate, CH2, let us say I will put it methyl ester, of course let us say maybe triethylamine little bit. So, you get a product B, fine. Write down the structure of the product B, of course you give the structure of A also. Huh? You tell me the structure with product B as well as A and B.